Hey everyone, this is Vijay. In this episode, we're going to talk about building ensemble models. Let's say you have a small circle of 3 trusted friends. We're going to call them the friend circle. You turn to them for advice, seek answers, and to solve problems. However, to err is human, and none of these friends are perfect. They all make mistakes, occasionally. Let's assume each member of the friend circle makes a mistake 20% or 1 in 5 times. You can ask them for advice on a project, or more quantifiably, just for this narrative, we can ask them a simple arithmetic question. Something like, is 12 cross 8 greater than 100? Each member can make a guess and answer yes or no, and you can do a majority voting for an overall friend circle answer. If all the members make consistent, unanimous decision every single time, then the error rate of the friend circle as a whole is 20%. You might as well, in that case, ask one member in the whole circle. But if each member's decisions are independent, and if their outcomes are not correlated, the friend circle makes an error only when more than 2 members make an error at the same time. We can calculate the error rate for the whole friend circle team. Here's the math behind it. We can calculate the error rate of the friend circle using binomial distribution. In binomial distribution, the probability of k successes in n independent trials, each with a success rate of p, is given by a probability mass equation that you see on the screen. Using the mass function, we can calculate the probability of the error for the whole friend circle, which is a grand 10.4%. So the error rate reduced from 20% to 10.4%, almost cut in half just by adding 2 more members into the group. If the members are independent, as we assumed earlier, we can reduce the error rate of the whole system. How can we have independent members in the friend circle? By having diverse members, so one is not influenced by other. Everyone has different background and different approach to solve a problem. We need to avoid group thinking. Folks, this is why diversity works. You now know the mathematical logic behind it. You can see a similar approach in everyday life. Board of directors, panels, advisors, ask the audience in the game shows, jury, courts, and your project teams. In the context of data science and machine learning, a group of models is better than one model. However, I left the most important question out. How can we promote diversity in a group of models? While individual members have biases and preconceived opinions, the thinking here is collective decision making is better than individuals' assessment of one person. That's the principle of ensemble learning. Ensemble learning is used to improve the error rate and overcome the biases of the individual models. They can produce one strong learner by combining many weak learners. However, some important criteria to note. Each member of the ensemble should be independent. The individual model error rate should be less than 50% for binary classifiers, that is, better than a random guess. There are a few ways we can build diverse independent models for an ensemble. Number 1, changing the training record set. Since the training data is the key contributor to the error in the model, changing the training set to build each base model is one effective method for building multiple independent base models. Number 2, changing the attribute set. Similar to changing the training data, where a sample of records are used to build each base model, we can sample the attributes for each base model. This technique works if the training data have large number of attributes. Number 3, different model algorithms. The same training set can be used to build different classifiers such as decision trees, using multiple algorithms, naive Bayesian, KNN, and artificial neural networks, etc. Number 4, changing the parameters within the models. Changing the parameters like depth of the tree, gain ratio, maximum split for a decision tree model can produce multiple decision trees with the same training set, and each is a bit different. Time for an actual implementation. All we need is a data set. We're going to use Iris dataset, and we're going to make use of multiple algos there. A data science tool. Time to fire up RapidMiner. Let's start with creating a very simple decision tree process using Iris dataset. Iris dataset is available under sample folder, and let's see how the data looks like. This dataset has about 150 observations with 4 columns which indicate the length and width of the flower, and the label is 3 species: Iris, Setosa, versicolor, and virginica. Let's go back to the process and add more operators. The first thing I want to add is a decision tree. To create a model, I'm going to leave the default parameters here, and then apply model. I'm going to use the same dataset to create both test and training dataset, so I'm going to use the split operator. One part of the split operator is used for training and the other one for testing. I'm going to split the dataset into 60% for one and 40% for another. So 60% of record goes to decision tree building and 40% goes to apply modeling. Let's connect this to the output. And we can also add a performance operator as well to evaluate the performance of the prediction. And we'll connect all the output. Cool. Let's run the process. So we have the prediction for about 40% of records, which is about 60 observations. So this is the original label and this is the prediction. And we have the decision tree here and the performance vector. So our prediction is about 91% accurate. So this is a very simple decision tree model. Now we can convert the same process into Ensemble by adding more modeling operator here. So we can replace this operator by adding Ensemble operator under modeling, predictive, and Ensemble. I'm going to first start with multi-voting. So this is a meta operator, so double click on this. We can add more modeling operator starting with decision tree. So I'm going to add a decision tree and a neural network, and we'll throw in a Bayesian modeling as well. So the same training set is used to create multiple models, and the overall prediction of this ensemble will be the majority of the prediction by individual Bayes classifiers. So let's run this process. So let's first have a look at the modeling operator here. So model 1 is a decision tree, model 2 is a neural net, and model 3 is a naive Bayesian. Stacking model is going to evaluate the majority of all 3 models. Our prediction has slightly increased from 91%, so Ensemble has a better accuracy compared with the Bayes model. So that's how Ensemble model works. If I relate to my previous anecdotal example, the independent members of the friend circle are 3 different models here, and this meta operator behaves as one modeling unit. And in this case, we have used the same training set to develop 3 different models. Alternatively, we can manipulate the training data set to create independent models as well. That's how bagging operator or bootstrap aggregating operator works. Or in the case of random forest, both rows and the attributes in the datasets are sampled and manipulated, and multiple independent models are created. So that's a quick, simple summary of ensemble modeling. Thanks for listening.